Hello, is everyone here? Did you listen to my voice? Can you hear me? Erin, are you okay? You survived?
Hello, miss.
Did you listen my voice?
Yes.
Okay, let's wait for your friends for another 5 minutes. Only then we start our class. Please do inform your friends who are not here yet to came into the class because I'm not going to repeat this thing. Okay? Okay, guys, good morning. So, going to proceed with our chapter 2C about the numbering system, and then I will go into chapter 3. Okay, so chapter 2B and continuation of chapter 2A, I've already covered with SCSJ students. Okay, and recording I also already uploaded into the YouTube. You can refer to the YouTube, or you can go to the Teams under files under recording. Okay. So to ease your life, I suggest you to go directly to the YouTube lah. Because it no need any request for access. Okay, because I know some of you unable to access the Teams. I'm not sure why. Okay, because if you already provide me your emails, it shouldn't be any issues for you to access everything through the Microsoft Teams. Okay, so let's continue with chapter 2C, which is about the numbering system. Okay, so in numbering system also we will implement it inside your digital circuits. Okay, so digital circuit will implement a core functionality of the architecture. So this would be your architectures. Okay, the figure 1 would be the circuits. Okay, abstracted from the implementation. So the circuit is represented as a black box, okay, labeled with its functionality or name, and only its input and output will be shown. Okay, so the inside the black box, okay, you're going to have your arithmetics or logic gates, logic circuits. You're going to have your control circuits, and you're going to have your storage circuits. Okay. So these three types of circuit can be used independently, or you can combine them together. Okay, so these figures that you seen here actually is an examples of the circuit implementations. Okay, so where you have your NOT gates combined with your AND gates, NOR gates, and so on. Okay, so for this one, do you have any questions? No? Okay. So this is a multi-bit circuit for your arithmetics. Okay. So how does we identify it is a multi-bit circuit? Okay. So you can see here, you're going to have one, two, three. Three logic gates, okay, where each of the logic gates will have their own bit value. Okay, so as you can see, A and B, if they follow the first logic gates, okay, you will get an output X. And if you follow for the second logic gates, you're going to get the output Y. Okay, so this output Y would be the input for your output Q here. Okay, so this will be your third logic gates. Okay, so this would be your tables. Okay, so A and B, you're going to get X. A, what is this logo? What is this logic gate, guys? For the second logic gate, what is this name for? Anyone? British? Oh, British. Did you listen?
Uh, it's
What
all good, miss.
is a OR gate? So A or B, you're going to get your output Y. Okay, so X, Y, and then you're going to get Q. So this what would be the third logic gates? Junior, what would be the third logic gate names?
Nor, miss.
Huh?
Nor.
No. Okay, so good. At least you recognize the logic gates. Okay, so if I ask you, why does A B you going to get, if my A is 0, my B is 1, how come I get a 0 for X? Mahruh, I have my input A is 0, B is 1, X is 0. So how come my output of AB would be 0?
Miss, because both of the inputs are low.
Huh? Wrong. It is because we are having
And engage.
AND gate. Yes, AND gate. Okay, now I have questions. Why does my X is 0, Y is 1, my Q is 1? Mariam? Mariam,
Yes.
I'm asking you.
Thinking. Yeah, I'm thinking. Like,
Oh,
good.
what? I'm having X as 0, Y as 1, and why my Q is 1?
No.
Huh? Anyone can help Mariam?
Because it's a NOR gate, so the outcome will be inverse, no?
Yes, correct. Okay. So that is how you create a truth table from the logic gates. Okay, you have to solve one logic gate, only then you can solve another one. Okay? So here that's why they're known as multi-bit circuit of for your arithmetics. Okay? So now we are going into the ALU. So what is ALU? Anyone know what is ALU?
Is the arithmetic logic unit.
Yes. What does we use for arithmetic logic units? What is the usage of it?
Doesn't it do like calculations?
Okay, what else that they do in arithmetic logic units? So, I give you a task. I want you all to find out how does the ALU looks like? What would be the usage of ALU? Okay, so I give you around until 10:30 and then I will choose two people to share me the answer. Okay? Okay, guys. I want Aisha Shakur. Can you share what is ALQ actually and how was the architecture? Aisha Shakur.
Yes, miss.
What is the ALU architecture? What is inside ALU? Oh, why you keep silent? I already give you guys more than the time that I mentioned. It's already
Miss
10 minutes.
is a digital circuit that performs arithmetic and logical operations that like for binary numbers.
Is that all inside ALU?
Yes. Like,
Okay. How about others? Rafi, what do you find about the ALU architecture? Rafi. So Rafi is not answering. Kachan,
Hello. Okay.
I'm asking, what do you find for ALU architecture?
ALU architecture. Oh,
Uh-uh.
output. Okay, okay.
Architecture. Where?
Um, so you want the explanation, like it shows the inputs, processes, and outputs, and also the one more thing, storage registers, and like NOT gate is one of the transistors,
Mm-hmm.
and I guess that's it.
Okay, Kachan, what will be the function of ALU, Kachan? Kachan! Kachan is sleeping, guys. Okay, it's okay. Sanat, what would be the function of ALU?
Uh, it's like you okay, like for example, you got logic operations you can use for that, and then you also got like arithmetic operations like addition, subtraction, multiplication, and then you also got like comparison operations like equals or greater than. So like this ALU is to basically calculate those kind of operations.
Oh.
Correct.
Okay, thank you. So, as you can see in the figures that I have shared in the slides here, we have our accumulator, logic circuits, register, control unit, and memory units. Okay, so as the first step, the operations that will occur inside ALU is your CU will receive an instruction from your memory unit that specify what will be the number that being stored in your memory location. Okay, so this number that being stored in your memory would be added to the number that currently is inside your accumulator register. Okay, so once they added, okay, the value would be transferred to your memory from your memory to your B register. Okay, so the numbers inside your B register and the number in the accumulator, okay, would be added together in the logic circuit. So your logic circuit actually is your operation places where you can do the addition, subtraction inside your logic circuits. Okay, so the resulting of the sum is then sent back to the accumulator to be stored. After that, inside your accumulator will have an increment. Okay, so the new number would be remain so that another number can be added to it, or if the arithmetic processes is finished, it will transfer back to your memory to be stored. Okay, so far do you understand these stages? Do you have any questions? Do you have any questions? No? Okay,
Mm.
so Next, we will see about the one-bit equality circuits. Okay, so this would be an example when we have A equal to B. I hope you still remember this definition. Last semester, you already learned about proving, right? So this one actually want to show you that the value from A is equivalent to the value of your B. So, for example, here we have not A, not B will be N together. Okay. And then we have another one that is A and B. So, and then these two output X and Y will be used a logic gate that is named as OR to get the value of A is equivalent to B. Okay, so far do you have any questions?
No.
No. Okay. So this one, this is an example that is showing how was your one-bit equality circuits compute. Okay, start we will have a 0 input, okay, for A and 0 for B. The value will be propagated through the gates. Okay, to compute the correct output of value 1 for A is equivalent to B. Okay, so if you look at here, 0, 0, okay, and then you have an and, it will convert into 1. So 1 and 1, you will get 1. Okay, this one also, you were having the same input, then you have and you will get a 0. These two things you get an OR. So you will see that A is equal to B. Okay? So now I want all of you to do these questions now and illustrate the circuits. Okay? Are you guys done? Can I have Nishimura to share the answer of A, none B, including the circuits illustration? Nishimura.
Okay.
Mm.
Can I send by the group because I do it by paper
It's okay. You can use your phone to share me the screen. Also can.
phone? Because I'm doing this with the laptop.
You can share your screen. There is no issue.
No, I did it on paper, miss.
You can use your phone.
So can I just screenshot and send it to the group?
I don't want you to this screenshot inside the group. I want to see you do share it now. You can add call into your phones and then use your camera to show me what you have done for A non B, including the circuits illustration.
Okay, coming, miss.
Then I want Tyson Yu to show me A nor B and also the illustration. Zhen Ying, I want you to show me the A or B, including the illustration. Are you guys done, Nishimura? I'm waiting for you to share your answer.
Yeah, almost miss.
Tyson Yu and
Still
Zenying?
doing this.
Zenying?
Yeah, Miss, I sent it in the WhatsApp group already.
Share it here lah.
Oh, Miss, still got no access to chat.
No. You can share your screen. You can add to your phone. It's okay.
Oh, I did it on
Okay.
paper. Oh, sorry.
It's okay. Good. Why these two guys take so long, eh?
Wait, so can I send it into the group too, miss?
I don't want. I don't want. For SCSJ, I don't want.
Come on, please, miss it. This is
No.
way too
No,
complicated.
no. SCSJ, no. SCSJ
So,
must show it live. I don't
come
trust
on,
any of
miss.
you for SCSJ. Hurry up. Nishimura,
Yes, miss.
where's your answer? Hasn't
Um,
you? Wow, it's been so long. It's only 1, 2, 3, 4 answers along with the
no,
drawings.
it's not that the answer is difficult. To share the screen, to do this process is difficult.
It's not that hard. You can just add, you can join the link using the phone, and then you open your camera and switch your camera into front camera or back camera to show me your works. No need to screenshot. Hasn't you?
Yes, Miss.
Show me your answer. So long already. Even Zening already done.
Miss,
Yes?
I joined you in my phone,
Mm-hmm.
but I can't access to share.
You can't access to share.
Yeah, with my phone.
It's weird. Okay, it's fine.
So I'll just send it into the WhatsApp group then.
Okay, fine. Tyson Yu?
Miss is looking like this.
Can you show it? Um, oh. What happened to your circuit leg?
Hmm.
What happened to your circuit leg?
Mhm.
What happened to your circuit leg? Same goes with Nishimura. Your output, what happened to your output? Okay, thank you. So good job, everyone, even though it takes time to do it. Okay, so this is the answer. Did you get the same thing with mine? Others, except for Zenying, Nishimura, and Tyson Yu. Others, did you get the same thing like mine? So let's proceed to the arithmetic circuit. So arithmetic circuit actually is a logic circuit that perform arithmetic operation inside your digital computers. Okay. For example, you do the addition, subtraction, multiplication, and so on. So all of this will take place inside your logics, okay, inside your ALU. So the purpose it can perform 7 different arithmetic operation using a single composite circuit, where your arithmetic circuit are constructed using the same method that we use to construct your logic circuit. Okay, so it's just that we are having a MUX and also FA. Okay, these two things we will learn later. Okay, but still it using the same method that we do for our logic circuits. Okay, so for example, construct a 1-bit adder circuit with the truth table for a single addition which have two values of input. Okay, two values of output, where one is the sum of A and B, another one is for your overflow or your carry out. So table 1 would be the truth table for 1-bit add. Okay, so now I want you to try to draw it first and then fill in the answer at the sum and the carry out. Okay, it is the same thing like how you do inside your workflow last week that I have teach you. Okay, so now it's just that you move the value inside the tables and see. Okay, start to do it now. I give you 1 minute to do it. And then I want British to share me your answer. British, are you done?
No, miss.
No. Simple addition and simple addition only. Just you change the method from the working step into the table format. It's just that we don't have carry in. We only put the carry out inside here.
But you want me to draw the table, right?
You can use Excel also can.
Oh, but oh, can I draw it on my paper or?
Use Excel also can. Then you show me the screen.
Okay.
Okay.
Miss, let me join on my computer.
Okay. Okay. Where is British? British? Hello? Guys, where is British? Is he here?
I guess Miss he's gonna join from his laptop.
I see. Okay. So while we waiting for him, do all of you know how to do this? Is there any issues for you to do it?
So basically carry out is end gate, right?
Huh? We can do what?
No, the carry out to get a carry out answer is basically end gate, right?
Hmm. This one, I just want you to draw only, not to draw.
Oh,
Not to draw. I just want you to provide me the answers for sum and carry out only.
Miss, can you hear me?
Yes, I hear you.
Okay, wait, let me share my screen. Can see Miss.
Can?
Okay, Miss.
I think you are putting the wrong question.
Eh?
Oh.
Is it not this?
A is 0011. B is 0101. Ah.
Wait. Wait, can I see the question again, Miss?
Okay, can you see this?
Okay. Oh, okay. Sorry. Okay, wait, Miss. Okay, Miss. Wait, let me show you. Can see, Miss?
Yes. Okay. Good. Good job.
Yeah.
How about others? Do you understand what is your friend showing?
Yes.
Do you have any issues about that?
No?
Huh? You don't understand? Okay, the example is like this. So A, when we talk about sum, we must use a plus. Okay? So 0 plus 0, what we will get?
0.
Erin? 0. So is there any carry out that we need to bring to the front?
No.
So you put a 0. So 0 plus 1, what do we get?
1.
1. Any carry out?
No.
No. Next, 1 plus 0. What will be the sum?
1.
1. Is there any carry out?
No, that'd be 0.
No, 0. So 1 plus 1, what do we get?
Is it 1, 0?
1, 0. So we should bring down our 0. So where does our 1 would be?
Carry out.
Yes, in the carry out. So this one shall be named as what? Previously, I already told you. It is an overflow.
Flow.
Okay, so this one is the extra bit that does not fit inside our truth table. So we consider it as overflow or the carry out. Okay, do you have any questions as for now?
No.
So this would be the full tables. Okay, do you have any question for others? Do you have any questions? No? Okay, so next, for each output, sum, and carry out, create a logical expression when your output is 1. Okay, so expression are expressed as disjunctions of per row conjunction of your input values. Okay, so when you want to convert them to your logic gates. Okay, so how did you do it? So can you actually imagine that if we are using the AND gate and XOR gate to get your value just now? No, right? So actually you need to distribute it one by one, test one by one. Okay, so what will happen when exactly one of the A or B is 1 and your carry out A and B is both A and B are 1. So you have to test, okay? So that's why you need these tables. From these tables only, then you can convert into this type of circuits. Okay, so this one is known as 1-bit ladder circuit because we only add 1 bit at once. We did not run multiple bit. Okay, understand? So expression for carry out cannot be simplified. Therefore, we need to assume that we have a XOR gate that we can use to implement the 1-bit adder circuit. Okay, so actually sum is much more complicated but can be simplified. So when we simplify our sum expression, it will produce a simpler circuit design. Okay, so you need to understand that, okay, before we assume, okay, once we assume, so we need to know that usually some output can be expressed as A XOR B. So if we have an XOR gate or XOR circuit, it actually will expressing a process for addition, okay, which will produce a simpler adder circuit design. If not, you need to use AND or and NOT to implement your addition processes. Okay, so so this is the example of addition process in the circuit. So using this version of 1-bit adder, okay, so we will construct an n-bit adder circuit by feeding the corresponding operand bit through an individual 1-bit adder. So we will feed the carry out from the value, okay, adder circuit to your carry in value. So still remember what is the difference from carry in and carry out? Okay, so the 1-bit adder circuit for your 0-bit receive a value for 0 for each carry in from another part of your CPU circuitry that decodes the add instructions. Okay, so for example, this one A plus, this one is plus B, okay, you will get your summation value. Okay, so is there any Cout? Don't have, right? So we move to the next one. So there it will be no Cout. So we use 1 plus 1. Okay, so is there any output? Yes, so we have a what? We have a carry in. Okay, then we move the carry in into a carry out here. Okay, so you will see here as a 0. So 1 will be at here. Okay, so far do you have any questions? Do you have
No.
any question? So all of this you need to do one by one. Okay, so at the end of your story, you will produce a C out 1 because of 1 plus 1 you already have what we get. 1 plus 1, what do we get?
1 0.
1 0. So we bring our C out 1, right? Okay, then 1 plus 1, you're going to get 1 0 also, am I right? So you bring to the next one. So that's why you get a 1 as your C out here. So it will be your overflow. Okay, so do you understand this one? So this is how does it looks like inside your circuit. Okay, but when we convert into your normal workflow, it looks like this. Okay, so this would be your organ. This would be your addend. And you will get your sum. And you will get your carry in and also your carry out. Okay? So far, do you understand? Do you have any questions you want to add? So just now I mentioned to you about ALU, right? So here you can see that this mentioned for the organ, it will start inside your accumulator register, while for your addend would be inside your B register. So your sum, if we are not finished to use it, it will maintain inside your accumulator. But once you finish your process, this one would be moved to your memory for storage purposes. Okay, so far do you understand why do we need to learn about ALU just now? Nice. Hello?
Yes, miss.
Okay, so next. This one is when we convert into the versions of using a circuit, arithmetic circuit. So FA actually is stand for full adder. Okay. So far, do you have any questions? Do you have any question for this one? No? Okay, so how do we design a full adder version of your circuit? So it will look like this. So you need to construct a truth tables that showing various input. We're going to have your possible cases. Okay, so for example, you need to have your organ bit and addend bit along with your carry bit input. Okay, so all possible cases, it means that all of your bit that is possible to be done, which is 3 inputs. That's why you're going to get 8 possible cases. How do we get 8 possible cases? How do we get 8 possible cases? Do you remember that formula that I teach you last week? 2 to the power of n. So this n represent what?
Inputs.
Yes, represent your input. That's why you're going to have 8 possible cases because you have 1, 2, 3 input, which is your organ, your addend, and your carry bit. Understand? So why does this carry bit is important? Why? Anyone? What would be the logic we requires the carry in bit as our input? What would be the logics? Guys, huh? Let's ask your friends here. I want to know the answer from Pangxia. Pangxia.
Yeah.
Why does we need to have a carry in as an input?
Hmm.
Hmm? Why? Anyone know?
No.
Anyone can help Pangxia? Why do we need to consider carry in as our input?
Uh,
Others? Anyone can help? Why does we need to count the carry in as the input? Sanat? Oh, Sanat.
Because it might uh
In your?
it might receive a carry from the previous bit.
Yes, because it is the value that you carry from previous bit to be added into your organ and addend. Okay, still remember the calculation that we do 1, 0. Okay, for example, we plus 1 plus 0 is 1. What if we have 1, 1? So we're going to have our 0 and we have 1 carry. Carry? This one considered is what type of carry?
Carry out?
British? Carry out, and then we're going to have a value here. That's why this value will consider as your, this is your input. Okay, do you understand that? Guys, do you understand why it counts as your input value?
Yes.
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 So once you have this one, you need to do the constructions of your logic gate. Okay, so you need to have at least 3 input. Okay, so you're going to have 2 output, which is your sum of your bit and also your carry out bit. That's why we have a carry out and carry in. So this is your input as carry in. This would be your carry out as your output. Okay, without these two things, we only have A and B to produce a single output. Okay? So far, do you have any question for this one? So, this is the steps. How do we do a full adder flow? Okay. So, for example, we have a case and full adder must be add to this bit to produce a sum of 0 and we have a carry of 1. Okay, because there are 2 input, we'll need to design a circuitry for each of your output individually, starting from your S. Okay, this is your S. Okay, this will be your step 1. So step 1, you need to use the method of sum of product. Okay, so simplify your expression by performing the factoring. Okay, can you see? You do the factorization. So that's why last semester you need to have a strong foundation to do the proving. Okay, so once you do the factoring, okay, so you need to check whether they have this common expression or not. If they have, you need to use the parentheses to differentiate them. Okay, as you can see in step 3, okay, the first term in the parentheses should be recognized as the exclusive OR. combination of B. And your C in can be written as B XNOR C in. Metodology. Okay. So this one, you need to do the factorization and then you need to do the simplification. Okay. 3A, you do the factorization, then you change them into a simpler conversion. Okay, then we go for step 3B. Okay, we rewrite them into a simpler version. Okay, so we need to change the value B XOR C in. So it will become the value inside step 3B. Okay, X is equivalent to B XOR C in. So that's why you're going to see your B XOR C in would be an X. So that's why it become like this here. Okay. So once you change them, you can simplify them like this. Okay, do you know how becomes like this? From not A, then X plus A not A and not X. How do we come A XOR X? Still remember? Still remember, guys? So from this one, we can merge them and change it back to the B and B XOR C in. That's why they have the value like in step 4, replacing your expression of X. Okay, once you get it, okay, you need to consider the output of the truth table, alright, the sum of product expressing using C out. So this expression can be simplified using factoring method. Okay? So do you understand what is happening here? Guys. So now we have another example, an addition of the lowest least significant bit position of two binary numbers where there is no carry input to be added, and we only have a special logic circuit that can be designed where the designation would take two input bits A and B and produce the output, which is the sum, and also the carry out. Okay, it is simplified the expression for the S using the algebraic method. So this one known as a half adder. So this one actually is similar to your full adder, except it's only operate for 2 bit only. Okay. So far, do you have any question for this one? No. Guys, do you have any question for this one? Okay. So we finished for our chapter 2C. So now I'm going to proceed with your chapter 3. So chapter 3 is about switching. Okay? Switch. So switch is an electrical component that can connect or disconnect the conducting path in your electrical circuit. Okay? It can be done for interrupting the electric current or diverting from one conductor to another. So we have 4 types of main switch, which is single pole, double throw, single pole, single throw, double pole, single throw, and double pole, double throw. So there will be a differences between these 4 switches. So this one, as you can see here, this would be the representation of the circuits that we will use later on. Okay? So why do we need a switches? Because switches are used when we want to select between on and off, select only one thing from many things that we have. Okay, the switching may be required to turn on your device or turn off your device, to turn a signal whether it is on or off, to select which one of the several devices should be used, and to select which one out of two or more signals that we should use. Okay, so switch, it is the enable input and it also a control buffer. Okay, so when we talk about enable input, suppose we want to enable a we want to be able to switch your device on or off. So what will be the processes? Okay, so many of your devices actually will be provided with an enable input which can be used to switch them on and off. So when when the input is enable, okay, or we use the label as EN to set as 1. So actually your device will be switched on, and when it is set to 0, your devices will be turned off. So usually the circuit designer can design a circuit in which different devices are enabled by different signals at a different time. Okay, besides it is enable the input, it also acts as your control buffer where we want to be able to switch a signal on or off. Okay, so the control buffer actually is a device that implement the functionality where it will have two inputs, where n bit data in and 1 bit control, and you're going to have one output which is representing n bit data out. Okay, so this is the control buffer. For example, we have control input equivalent to 0, where this means that your data output floats. Okay, the signal is off. Okay, so when your control input is 1, okay, so how do we know? You look at here. If 0, it means that it will be off. If 1, it will having the data to be out. If your input is like this known as a floating, it means that you're going to have an error. Okay? For the controller inverter, it will be a reverse information from your 1 and 0. For example, 0 in your for your control input, it will change it into a floating signal or off. But if your control is inverted controller, it will become on. But if your input is floating, like this, floating, it will become an error. Okay? So next we have our decoder. A k bit input signal and 2 to the power of k times 1 bit of your output. For example, the k is 4. So we will count it like this, 2 to the power of k times 1. So we will get 2 to the power of 4 times 1. So what we will get? What we will get?
16?
16. So you're going to have around 16 output. Okay, this is how you calculate about the decoder. So the binary number is used to select which one of the decoder output is set to the 1, because you have 16 outputs. So we need to use the binary value to select which one of the decoder output can be set as 1. So usually has an enable input as well. When this is 0, all your outputs are 0. A k-bit decoder may be used to select one out of 2 to the power of k circuit that will be switched on, while others would be switched off. Understand? So next, decoder without enable. So the implementation will enforce the minimum term without summing them up. So that's why we need to have one and enable. If not, you're going to have a issue here later on. Okay? So far, do you have any question? So, take note that each of your minterm is connected directly to separate an output. Unlike a sum of minterm circuit, this one uses all of your minterm. For example, it is completed. Okay? So, next, decoder with enable. So, this purpose is to raise one of the 2 to the power of k output, where the rest of your output would be driven down, which is off lah. So your decoder operates when your enable signal is raised. For example, you have 2 times 4 decoder. That means that 2-bit input signal is used to raise one of the 4 output. Okay? So this would be the differences between when we put enable is equal to 1 and when enable is equal to 0. Okay? So, for example, this one, as you can see that when we have enables, okay, this one is the decoder without enables. So you can look at down here. We don't have any enables, no. So when we have an enables, it will have here at additional. Okay? So enable will be the input at the bottom. Okay? So then we're going to have our multiplexer, where this multiplexer is a multi-position switch, where it will use to switch between several different data sources. Bit is like a rotary switches found on the front of the some stereo amplifiers that can be used to select between your audio sources. So 2 kind of input that will be used, which is in data and your select. So your data inputs actually is your sources, while your select input sets the switch position. Okay? So the multiplexer looks like this. This is the logo of multiplex, the symbol or the icon that being used inside your logic circuits. Okay? So multiplexer, the k-bit select input is used to choose out of 1 2 to the power of k data input is passed through. Okay, so the number of the bit is then select the input, determine how many data sources may be connected. Okay? So far, do you have any question for this one? No? So our class will finish at what time, class? Hello?
12.
What will be the timing that we finish our class?
12, miss.
By 12. So you guys are still awake or not?
Yes.
Yes.
Yes, because we have another 31 slide to go for this chapter. Can you guys still focus? Okay, so let's proceed. Using a multiplexer, so a multiplexer is used to choose between your data signal. So 1 bit select is equivalent choose 2 data input, which is numbered from 0 to 1. If 2-bit select, you choose between 4 data inputs. What is the use of your multiplexer? To switch between circuit, between operations in ALU, to allow your data link to carry signal from different sources at different time. Okay? So, a multiplexer examples, would be the multiplexer example. So, in a processor with 4 data register, which it will temporarily your data being stored, we may wish to perform arithmetic operation on any combination of 2 of them. We use 2 multiplexer, one to select each operand. Okay, so both multiplexer have the same set of data input, and it will have its own 2-bit select input. So the 2-bit pattern selects which of the 4 registers would be used. So now we can select any combination of 2 data items for input to the processor's ALU. So now I will stop our lectures for chapter 3 here, okay, I will give you a task for you to find out actually where does this multiplexer being used and what would be the importance of the multiplexer in this subject.
It means
Okay?
I thought it's chapter 2C, you know?
Oh, this one is already chapter 3.
Oh, okay.
Okay, so I want you to find out and share your answer inside the WhatsApp group. Okay? So far, do you have any questions? No? So you have 30 minutes to find out all of this information. Okay? Once you finish, you can leave your meetings. All of you must share me the answer through the WhatsApp group. Okay? Do it now and share the answer inside the WhatsApp group.
Miss can write down the task in the chat again.
Excuse me, miss. Miss.
Huh. Any issues?
No, miss.
No. For SCSG student, for tomorrow, we're going to have our class online. Okay. I will do the record. You have to attend. For those who are free and not from SCSG, you are welcome to join the classes for tomorrow. If you're unable to join, still the same thing. I will share the YouTube. That's okay. I will share the recording through YouTube, so you may watch it via YouTube. Okay. So while you are searching, I will continue to finish the multiplexer part. So I will continue about demultiplexer for tomorrow. Okay, so we have only 2 slides more. So multiplexer examples in a processor with 4 data register. Okay, this one I already mentioned just now. We may wish to perform arithmetic operation with on any combination of 2 of them. So we will have 2 multiplexer where both multiplexer have the same data input. As you can see here, your multiplexer value would be different. One here is 0, 1, and this one would be 0, 0. So you're going to have to do the multiplexing with the input here. Okay? Multiplex with these two things and you will get this kind of value. Okay? Then these two things would be add together and produce your carry out and produce your output here. Okay? So far, do you have any questions?
No.
No? No? Okay. Then, what will be inside your multiplexer? So usually your multiplexer will have 4 times 1 bit data input and 2 bit select output. So a decoder is used to switch one of the AND gate arrays and it 1 bit output drive the AND gates on the right side. Okay, so 1 times 4 output OR gate gathers the output from the individual AND gates. Okay, like this one lah. You have 4 input. Okay, so it will gathers your individual from your individual gates. This one is your AND gates. Okay, so you go from this AND gate, you're going to have 4 output, right? So this 4 output will become your input of your OR gate. Okay, so each of these is 2 input AND gate with a decoder output used as the control to each of your AND gates. Okay, still remember about the gating last week we have learned. So it used the same information. Okay? So, this is the example where you have 8 times 4 input OR gate array. Okay? So, a decoder is used, as I mentioned previously, a decoder is used to switch on the AND gate arrays. So, still, do you know what is array? Do you know what is array? Okay. It has 1 bit output that are split into 8 to drive the get arrays on your right. Okay. And then each of these is an 8 times 2 input AND gate array with a decoder output used and a control input to each of your AND gate. Okay, 8 times 4 input OR gate array will gather the output from individual get arrays. Okay. So far, do you have any questions? No. So we will stop here. Have you done with your task that I have given to you?
Almost done, miss.
Almost done.
Mm.
Since you say you almost done, can you share what is your findings?
I
Hello?
just I just write in Microsoft Word, can, right?
Can. You can share your screen.
Miss can see, right?
Okay, so can you explain a bit? Yes, already know the.
Okay, so of course I ran a research in ChatGPT. So they say the importance of multiplexer. What I know is that it actually saves the hardware resources. So like how? Because it only uses only uh one output line, and then like I write here, it allow multiple signals to share one medium. So basically, what uh, is the importance of multiplexer is also efficient data transmission. And then I also write down here helps control data flow. What does it mean? It basically helps control data flow in like communication, computing devices, and embedded systems. And then the next question you ask me to do is how it looks like. So basically, I went to Google, I searched uh, how does the multiplexer looks like, and most of the pictures it pops up like this lah. And then the third question, how is a multiplexer used or implemented? Uh, for now, I put CPUs because the others I don't understand. But they said that it also how is a multiplexer used is also can be used in computers, used in ALUs to select which operation is to perform. And then I wrote down here only CPUs because this is the only part I understand. It uses root data from different registers or memory locations. And then the last question is relation between multiplexer and basically the subject from Silicon to see is hardware logic. Basically, what does hardware logic means is basically the multiplexer is built from logic gates like AND or NOT, which are made from transistors. And then you got digital design, which is basically how it relates is it basically learning how data moves through a system, which helps you understand how code becomes like machine actions. And then you got data flow. Data flow when writing code in C, you might use like conditions like if or else. And then at the hardware level, it performs like a similar logic, choosing between values based on like control inputs. Yep.
Oh, okay. So good. What about this? How about Marcia? Can you share me what is your findings? Hey, Marcia, I'm waiting for you to share what is your findings. Okay, so thank you, class. See you when I see you. For SSG, don't forget for your class tomorrow. Bye.
Thank you, Miss. Bye, Miss.
Thank you, miss.
Bye, miss.